Okay, we're recording. All right. This is our last chapter of the course, chapter 18 on redox reactions, also known as electrochemistry. This will come back after the break, after spring, Thanksgiving break. And that first Tuesday back, we'll have a review on this chapter. And then that following Thursday, we'll have the exam on this chapter. Then the week after that is finals. We'll have a final exam on that Tuesday, same time, same station. Just show up at your regular time on that Tuesday, the week after, the second week after Thanksgiving break. And the final exam will be comprehensive. It's not going to try to be a knockout punch, but if anything that we've covered up to this point in the whole course is fair game. And the weight of the final exam is the same as any exam. It's not weighted any heavier than a normal exam. Okay, well, let's take a look at redox reactions. This one's working. That one's working okay for now. Let's see here, redox reactions. So what do we mean by a redox reaction? Any type of reaction which involves the transfer of electrons between two reactants will fall into this category. One example that's given here is the reaction of sodium metal and chlorine gas. These are two elements, and at standard temperature and pressure, sodium will be a metal, chlorine will be a gas. And when they react, they produce sodium chloride, table salt. So what has happened here? Well, the elements in their natural state, in their standard states, are neutral. We know that. They don't have, sodium would have 11 protons. So that means it would have 11 electrons, right? Chlorine, each one of the chlorines would have 17 protons, so each one would have 17 electrons. All right? So to balance, we need two of those and we need two of these. And over here, we know from when we were writing chemical formulas, we knew that the chlorine, when it's in a compound, has a -1 charge. And sodium has a +1 charge because sodium is an alkali metal, chlorine is an halogen. All right? So what we've seen is these are both neutral to start with, and they end up with a charge in the compound. So what has happened? What has actually happened is electrons have been transferred. The chlorine will accept an electron from the sodium. And in fact, since there are two sodiums, 2 electrons have been transferred. And now that we have 2 sodiums on this side and 2 chlorines on this side, this chlorine has an extra electron. So if it starts off with 17 as a neutral, then it's going to end up with 18 electrons in the compound. And since sodium starts off with 11 electrons when it's neutral in the compound, it will only have 10 electrons. And remember what I've said before, when you can tell an element by the number of protons it has. But when you put a charge on an element, You don't mess with the protons. If you change the number of protons, you change the element. So the only way you can change a charge is by the balance of protons and electrons. And if we start off with 11 protons and 11 electrons, it's balanced neutral. But if we end up with 10 electrons, we're short one negative charge, which gives you a net positive charge for sodium. And by the same reasoning, 17 electrons in chlorine to 18 electrons in chloride in the compound will give you a balance of one extra electron for the chlorine. So the transfer of electrons in this case has shown us that we have an oxidation reduction reaction. Now, when we say oxidation reduction, we probably should define our terms. So oxidation is loss. Loss of electrons is an oxidation. Whereas reduction is gain of electrons. Oil rig. Oxidation is loss, reduction is gain. So, which one of these has been oxidized and which one has been reduced? Well, since sodium lost an electron, it was oxidized. And since chlorine gained an electron for each chlorine atom, it was reduced. All right? You just have to learn the terms. Oxidation is loss, reduction is gain. Okay. One other point to make here. Whenever an oxidation occurs, a reduction has to occur. They always occur in pairs, never by themselves. So if you have an oxidation, you have to be able to provide a reduction. So here's another example. I'll leave that mnemonic up there for now. So here we have 10 with a 2+ charge. That's showing up, yeah, that's showing up. And we have iron with a 3+ charge. Okay. And the products are 10 with a 4+ charge and iron with a 2+ charge. All right. Now the trick is to tell which one is being oxidized and which one's being reduced. We know that an oxidation reduction has taken place because there's a charge difference. This 10 is 2+ here and 4+ there. The only way that can happen is if electrons are transferred. So how do you go from a 2+ to a 4+? You add electrons or subtract electrons? Subtract, right. This one had to lose electrons. To go from there to there, we had a loss of 2 electrons per 10, right? And since there's only one of them, we have a total loss of 2 electrons in that reaction, okay? So now we know that this one was oxidized. That means this one has to be reduced. And if it's reduced, it has to gain electrons. So if we go from here to here, what has happened? iron has gained 1 electron from 3 plus to 2 plus. 1 electron per iron atom. But we've got 2 iron atoms. So 2 electrons were lost here and 2 electrons were gained there. That always has to balance. The total number of electrons lost has to equal the total number of electrons gained. And we just showed it. Okay? So in this case, the 10-2, which is this one, was oxidized. Now, a short discussion on oxidation states. Oxidation state is a bookkeeping method so that we can keep track of our electrons. We know where they're going and where they left and where they're ending up. So we need some rules for how to determine oxidation states. Now, oxidation states for an ion, easy. A single element, atom with a charge, its oxidation state is the charge. So 10, 2 plus, its oxidation state is 2 plus. Right? That's easy. But some elements have an oxidation state and it's not explicit. Such as, well, if you have the compound, and that was crapping out on me. Let's see. Green doesn't show up too well, so I'm gonna have to go back and forth with these guys. In that compound, it's not explicitly given, but we know that sodium is an alkali metal. So in the compound, it's going to have that charge. Chlorine's going to have that charge. Now we can tell the oxidation state. The oxidation state here is +1. Oxidation state there is -1. Okay. So the rules. First rule: if you have an element, just a written element, and it's simple, its oxidation state is 0. All elements off by themselves have an oxidation state of 0, as long as they are in their natural state. In other words, standard state. Temperature 25 degrees, atmospheric pressure 1 atmosphere. So this one would be chlorine gas. It's a diatomic, so each one of the chlorines would have a 0 oxidation state. And that's based upon their neutrality. They have the same number of protons, same number of electrons in this standard state. Any monatomic ion, and we know that in solution, right, these guys are independent ions, right? So if they're in solution like that, it's easier to tell what their state is, because they're separate ions. So that ion is a +1 state, this one's a -1 oxidation state. That's the second rule. When we put oxygen in most compounds, it will be a 2- oxidation state. And that just goes back to our rules for groups. Like compounds that are made with halogens are -1, compounds that are made with chalcogens are -2, and so forth. So we give oxygen, when it's in a compound, we give oxygen a 2- oxidation state with one exception. If oxygen is bound to itself and then bound to other things, we have a peroxide. And a peroxide bound to something here, bound to something here. Each one of these peroxides is -1. So both of them together, each one of those oxygens, so the peroxide is a -2 total. Okay, so whenever you have a peroxide sitting on your medicine shelf, hydrogen peroxide, hydrogen, hydrogen peroxide, H2O2 is hydrogen peroxide. The oxygen in that compound is a -1 oxidation state. But everywhere else, we assume that the oxygen in a compound has a 2- oxidation state. Most compounds in which we find hydrogen, and these are covalent compounds, it will be given a +1 oxidation state. Now, here's the first introduction of covalent compounds explicitly, where we have an oxidation state. So the compound doesn't have to be ionic. It can be covalent, and we assign an oxidation state to each of the atoms in the compound. So a perfect example there is water. Right? We know it's a covalent compound, and each one of these hydrogens is a +1 oxidation state. And the oxygen, according to the rule before it, is a -2 oxidation state. So we find that 2 times +1 is +2, balanced by -2, so it's neutral. Right? That doesn't mean that hydrogen has to stay +1. But if hydrogen is in a covalent compound, we assume until we're told otherwise that it's a +1. There are some compounds in which hydrogen can assume a -1 charge, but those are ionic compounds, and I'll point them out to you when and if we get to them. Fluorine is a -1. It's always a -1. And if you look at your review document and the periodic table at the back, you'll see listed in the periodic table. Let's see, I have to find one first. And where did it go? Here it is. You'll see in the on the right-hand side of each one of the boxes with an element, you'll see a list of charges. Those are oxidation states. The ones we're interested in primarily will be the first one that's listed for each one of those. But those other oxidation states are possible depending on the compound. So the trick is, when you have a compound and you're trying to determine what the oxidation state is for each element, you want to go to these rules and assign those values for these first elements. And then you calculate the rest of them. So we'll do some examples, and hopefully it'll become obvious how we deal with them. If you have a neutral compound, like water, the oxidation states added up for every element in the compound must be 0. Neutral compounds have a summation of oxidation states equal to 0, always. If you have a charged ion, like a polyatomic, like nitrate, when you add up the oxidation states for each one of these elements in that polyatomic ion, they have to add up to the charge on the ion. Right? So if we assume that oxygen, according to rule number 3, if we assume that oxygen is a -2 oxidation state, we have 3 of them, so that means total they're -6. Right? And we have to hold one of these negatives out for that charge. That means we only have to balance a -5 with the nitrogen. So the nitrogen would be a +5 to balance that -5, and that would leave us with an extra minus there. And to verify it, You just say 3 times -2 is -6, -6, and a +5 is a -1. And we've satisfied the conditions for rule number 7. Okay? Alkaline metals are all +1. Alkaline earths are all +2. That simplifies things there also. And the rest have to be calculated. All right, so we'll do some examples so you can get some practice calculating oxidation states. Now, if the question hasn't already struck your mind, you may wonder why we need to bother with oxidation states. Like I said at the beginning, it's a bookkeeping scheme, keeping track of your electrons, where are they going. If you don't know where your electrons came from and where they went, there's no way that you can follow a redox reaction. You have to know where the electrons are going. So the first thing to do is find the oxidation states for all of your elements. K2Cr2O7. Okay, oxidation states. We start with the ones we know. The alkaline metals are all +1. Okay? So each one of those potassiums is +1. That means we have a total of 2 pluses for potassium. Oxygens we give a -2. Okay? So we have a -14 here. Total, 7 times -2. Now we can use these to tell what chromium is. So what's the total of 2 plus and 14 minus is 12, right? 12 minus. So what we have to do to make this compound neutral, since we have 12 minuses between potassiums and oxygens, these chromiums have to balance with a total of 12 pluses, right? And since we have 2 of them, each one is a +6. Okay? It's simple math. Okay? So the way this animation works is the first ones that are shown are the ones that are assumed for the alkaline metal and for oxygen. And then we calculate the one that's left over. And if you look at your periodic table, in the chromium is the 6th one over in the 4th period, you'll find that it has a possibility of +2, +3, and +6. Those are the most common oxidation states. And this one in that compound is a +6. Okay, how about carbonate? Carbonate is a polyatomic ion with a 2- charge. So if you start with the one we know, which is oxygen, which is 2- for each one, which means 6- total, right? And we've got to be sure that we have 2 minuses left over. So we're balancing 4 minuses, because 2 of those minuses are reserved for that charge. So now that means carbon has to be a +4 to balance that -4. Okay? And if you look at carbon, you find that it can have several oxidation states. -4, +2, +4 are the most common. And we can do the same thing for manganese 4 oxide, for phosphorus pentachloride, and for sulfur tetrafluoride. We just start with the ones we know and calculate the others. Okay, any questions? So that's our bookkeeping. Once we figure out how to calculate oxidation states, then we can tell whether or not, first of all, whether or not we actually are talking about a redox reaction. There's some reactions where electrons don't transfer. In those cases, we don't have a redox reaction. But the only way to know for sure is to calculate the oxidation states and see if any of them have changed for any of the elements from reactants to products. So for this one we talked about earlier, these elements, oxidation state 0 for sodium, 0 for chlorine, +1 for sodium, -1 for chlorine. That means that sodium is oxidized. And in addition, we have another set of terms for sodium plus chlorine. If sodium is oxidized and chlorine is reduced, that means, and they always occur in pairs, the agent that caused the oxidation of sodium was chlorine. So it's the oxidation, well, actually, oxidizing agent. And the sodium is the reducing agent. Okay. So once you figure out sodium is oxidized, it automatically becomes the reducing agent for chlorine. It causes the reduction of chlorine by transferring electrons to it. And conversely, chlorine is the oxidizing agent, which has been reduced and is serving as the receptacle for the electrons coming from sodium, which makes it the oxidizing agent. All right. So how about this one? Let's see. We've got some on order, but they haven't arrived yet. I'm having to make do with these old ones. So if we have methane, which is burned in air, it yields carbon dioxide and water. Okay, so how do we tell if this is an oxidation reduction reaction? Well, there's a quick way, actually. If you have an element on one side of the reaction, like we do here with oxygen, and it turns up in a compound on the other side, you automatically have an oxidation reduction reaction. If we had an oxygen on this side as an element, and it came from a compound, same story. If it changes from an element to a compound in the process, then you have an oxidation reduction. Now, that doesn't mean that you always have to have an element there. But if you do have an element on one side, ends up in a compound, it has to be oxidized or reduced, one or the other. But if we do our bookkeeping, oxygen is a 0 oxidation state. What's hydrogen? In a covalent compound, it's +1, right? So that means we have 4 pluses that have to be balanced by 4 minuses, and those 4 minuses belong to 1 carbon. So that carbon is a 4- oxidation state. On this side, oxygen is 2-, which means 4- total, and this oxygen is 4+ to balance those 4 minuses. And on this side, we did these already, -2 here and +1 there. All right, so now we have all of our oxidation states identified. We can decide which one's reduced, which one's oxidized. So which one got reduced? Which one did we? Reduction is gain, oil rig. Reduction is gain. Oxygen went from 0 to -2. So oxygen was reduced. So we have a gain of 2 electrons from 0 to -2 per oxygen. And how many oxygens are there? Well, actually, oxygen went 2 places, right? It went 2- over there, 2- over here, and we've got 2 there and 2 there. So we have 4 oxygens that gained 2 electrons each. So we have 8 electrons transferred there. For this one, the carbon was oxidized. 4 electrons. Actually, how many electrons were transferred? If you lose 4 electrons from this carbon, you end up where? 0 oxidation state. Then if you go from 0 to +4, you lose 4 more, don't you? So from 4- to +4, you actually lost 8 electrons. Per carbon, times 1 equals 8 electrons. So we gained and lost the same number of electrons in this process. Okay? Oops, I went too far. Back up, back up, back up, back up. It's not going to make it easy on me, is it? There we go. Okay. So here we have a set of 3 reactions. The first thing we have to do is decide, is the reaction oxidation reduction? Well, the first one, notice, you've got an element here, it ends up in a compound. And you got a compound with this element, ends up as an element here, a free element. Okay, so we know that one is an oxidation reduction, no question. The question is, which one's the oxidizing agent and which one's the reducing agent? So if we go from zinc plus hydrochloric acid yields zinc chloride and hydrogen gas, which one has been oxidized? Well, this one's 0, and that one's 0 oxidation state. This one's a halogen, and this hydrogen is +1, so that's a -1. This one is a -1, and you got 2 of them, so this one has to be a 2+. Right? So which one was oxidized? Well, we went from 0 to +2, so that one is oxidized. And this chlorine didn't change, right? But the hydrogen did. The hydrogen went from +1 to 0. So it was, it had to add an electron. So it gained, which equals, it was reduced. Okay? So now we've decided which one's oxidized and which one's reduced. Now which one's the oxidizing agent? This one is the oxidizing agent, because it caused the oxidation of zinc. And this one is the reducing agent, because it caused the reduction of hydrogen. Okay. So that one's the reducing agent, it's in red. And that one's the oxidizing agent in blue. Okay. So if we go and determine the oxidation states for every element in this compound, this reaction, we find that oxygen's 2 minus, right? It hasn't changed. They're all in compounds, so we can assume they're 2 minus. That means this hydrogen is +1, this one's a +1. We did this one earlier. That chromium is a +6. What's this chromium? Well, how many minuses here have to be balanced? -2 times 4 is -8. But we need to hold 2 of them out, right? So it's, instead of a -8, it's a -6 that has to be balanced right there. So that chromium is also a +6. It didn't change, right? So this is not an oxidation reduction reaction. Even though we've got all those charges floating around, nothing was oxidized, nothing was reduced in the process. They just swapped places. Now this one, we've got an element over here with a 0 and a compound over here, so we know that one is an oxidation reduction. No doubt about it. But notice what happened. We had 2 coppers over here. What's the oxidation state on that copper? Well, if this is a -1, then that one has to be a +1. Right? So this copper is a +1, but it goes 2 different directions. One of these coppers, see there are 2 of them? One of these coppers ends up at +2, and the other one ends up at 0. So one of these coppers was reduced, and the other one was oxidized. Right? That's a special case of an oxidation reduction reaction. It's called, well, let me get one that writes. It's called disproportionation. Now, it looks like that compound went 2 different directions, like it just split personality. But actually, one of these compounds was the one of the 2 was the reducing agent, and the other one is the oxidizing agent. Okay? So you got them both here. And another way to write that would be like this. Oops. You could write it like this. Now you can say this is the oxidizing agent, and just pick one. And this is the reducing agent. To produce your products. Okay?
Trying to figure it out faster.
Yeah, I mean, you just split these out. I mean, just because it says 2 here doesn't mean you can't write it like that. Right? There's one of them, there's the other one. One of them is the reducing agent, the other one's the oxidizing agent in a disproportionation reaction. This is one of the reactions that takes place in the smelting process for purifying copper from its ore. You just heat it up and it reacts with itself. Okay. So we've had these example reactions that were balanced for us from the beginning. We didn't have to balance them. But if we're given a word problem, and you say such and such reacts with something else and produces products, and they're in words, then you got to write out the compounds, and you've got to balance the equation. So whenever you have an oxidation reduction reaction, it's best to use a different method for balancing than we had in the past. In the past, we used the budgeting process for balancing our reactions. And sometimes for redox reactions, that will work. Sometimes it won't easily. So half reaction method is an alternative way of balancing reactions. So what do we mean by half reactions? Well, we use the concept of oxidation reduction. You set up one reaction as an oxidation, and you set up a separate reaction as the reduction. Once we've identified which was oxidized, which was reduced, then you can set up the half reactions as separate reactions. Balance the half reactions, and then put them back together. Okay, so we have steps that we go through. Now this one is already balanced, but it's balanced so that I can show you which is the half reaction for reduction, which is the half reaction for oxidation, before we actually go in and do a balancing process. Right? So this is the balanced equation. There's your reactants, there's your products. And we do if we do the budgeting for our oxidation states, then we find out which ones were reduced and which ones were oxidized. We find that this manganese goes from +7 to +2. So it had to be reduced. We had to add 5 electrons to each manganese. So our reduction half reaction will include this one and that one. Our oxidation half reaction is centered on iron, going from 2+ to 3+, right? So it lost an electron. It was oxidized. So the iron from this one to that one will be part of our oxidation half reaction. Right? So there's our reduction half reaction. And there's our oxidation half reaction. Oops. Notice that when we write the half reactions, we also include the electrons. Right? So for this reduction half reaction, we know that the electrons have to be on the reactant side because they are added to the reduced element, right? We're going to add these electrons to that manganese, and that puts us over here. 5 of these negatives to that +7 gives us 2 pluses. So the reduction half reaction has the electrons on the reactant side, and the oxidation half reaction has the electrons on the product side. Okay? Now, the question you may be asking yourself, how did we know to put the hydrogens here and the waters there? Well, that's part of the balancing process. I'll show you how that works in just a minute. These are the steps that you go through when you're doing a half reaction balancing two-step. You identify, you write the equation, and then you pull out the oxidation and the reduction half reactions with only the elements that are being oxidized or reduced. Right? Then you take your the half reaction and you balance all the elements except hydrogen and oxygen. You leave those alone. And the reason we leave those out is because we may have to add water somewhere. Right? So since hydrogen and oxygen are part of water, we just leave them alone to begin with and balance only the elements that are not hydrogen and oxygen. Then we stick the oxygen in wherever it's needed and the water in to balance the oxygens. I'll show you how that works in just a minute. Then, if necessary, you add protons on one side or the other to balance the hydrogens that you just put in there with water. And this is called the acidic half reaction method. That's the one we're going to learn first in acid solution. Then you balance the charges. Then you put electrons in order to show oxidation or reduction, depending on which reaction you're dealing with. And then once you get those balanced, you balance the number of electrons for each of the half reactions, right? So if you have 2 here and 4 here, then you have to take 2 times the entire reaction to get 4 electrons. You can't add them back together until you get the right number of electrons, the same number for oxidation and reduction. Then you can add them back together. And then you check to see if it's correct. Okay, so here's our example. Let's see. Okay. So here we have a reaction that's not balanced. And what we want to do first is decide what are the oxidation states, so we can tell which is the oxidation half reaction and which one's the reduction half reaction. So we've got chromium, dichromate ion plus the sulfite ion yields chromium 3 plus sulfate. Okay? So we did this one earlier, and that gave us +6 for that chromium. Right? And this one is a +3. So we know going from +6 to +3 is a reduction. We had to add 3 electrons for each chromium to go from this one to that one. So our reduction half reaction is going to have dichromate on this side and chromium 3 plus on that side. Okay. In this one, oxygen is 2 minus, so there's 6 minuses total, and we have to hold 2 of them out to keep that charge. Right? So we really only need to balance 4 minuses. That'll give us balance all the oxygens with 2 minuses left over. This one we have 4 times 2 minus, which is 8 minus. Hold out 2 minuses for that charge, and this one is a 6 plus. So in this case, the sulfur was oxidized from a +4 to a +6. Okay, so this one, the oxidation half reaction is sulfite with a 4 plus sulfur going to sulfate with a 6 plus oxidation state. Okay? So now, what's next? Balance all the elements except for oxygen and hydrogen. Right? So, we've got 2 chromiums here. We need 2 chromiums over here. That's it for that. We've got 1 sulfur here, 1 sulfur there. It's already balanced for sulfur. Now, how do we balance the oxygens for this one? You start with water. If you've got oxygen on this side, you need oxygen on that side. Right? But how many oxygens do we need? We need 7. We need 7 oxygens on this side. Okay, so that's 7 oxygens here, 7 oxygens there. Now what have we done? We've introduced hydrogen into this process. So for acidic solutions, we add protons on this side to balance those hydrogens. 14 hydrogens, right? So now we have 7 oxygens and 14 hydrogens. So the hydrogens and oxygens are balanced. Okay, so let's do this one. We've got 3 oxygens here, 4 oxygens there. We need a water on this side to give us 1 oxygen more to balance the 4 oxygens. Now we've added 2 hydrogens. We have to have 2 hydrogens on this side, and we add those as protons. Okay, so now we've got oxygens and hydrogens balanced for both half reactions. Now we have to balance the electrons. So if this one was reduced, that means the electrons are going to be on this side. We're adding electrons here to give us 3 pluses on that side. So how many electrons were actually transferred? If this is 6 plus, we have 12 plus here, and we're going to 6 pluses over here, 2 times 3 plus. So we actually transferred 6 electrons. 6 negatives will neutralize 6 of those positives and leave us with 6 positives over here. So we need 6 electrons there. Okay, how about this side? We went from 4 plus to 6 plus. So we actually we lost 2 electrons in the process. Okay. Any questions so far? Takes a little practice. Okay, now before we can add these back together, we have to balance the electrons. So this one transferred 6 electrons added in here for reduction and 2 here for loss. So how can we get 6 electrons out of this one? Multiply the whole thing by 3. So that gives us 3 sulfites plus 3 water and 3 sulfates plus 6 hydrogens plus 6 electrons. Now we can add these 2 together because our electrons balance. We added 6 in here, lost 6 there. Now you just bring everything down. So we have dichromate, one of those. We have 14 hydrogens. The electrons are already canceled, right? So we don't have to bring those down. And still on this side, we have 3 sulfites and 3 waters. So that's everything on the reactant side. Product side, we're going to put these 2 together. So we have 2 chromium 3 plus and 7 waters here. And then we have 3 sulfates, 6 hydrogens. And the electrons are already taken care of. We already canceled the electrons. Okay, so that's everything we have in those 2 half reactions brought down. Now what you do is you look for same thing on both sides. Right? So we have 14 hydrogens on this side, 6 on this side. Right? So these go out, and they came from these, right? So that's what, 8 hydrogens on that side left over. And then waters. We've got 7 waters over here and 3 over here. So these 3 go out, And that leaves us with 4 waters on this side. So our reaction is going to be balanced. Now it's balanced. 1 dichromate plus 4 hydrogen for 8 protons plus 3 sulfide ions yields 2 chromium-3 ions plus 4 waters plus 3 sulfate ions. That's our balanced equation. And these are the steps, if you like animations. Everything that we did here is there. So we should end up with, let's see, there we go, 14. No, we're not finished. Next slide. Here we go, balancing the electrons. Here we go, combined equation. And the final balanced equation is that one. 8 hydrogens, 1 dichromate, 3 sulfites, and then 4 waters, 2 chromium-3 pluses, and 3 sulfates. That's your balanced equation by the half reaction method. And this is the half reaction method for acid solutions. Right? So you may guess that there's also a half reaction method for basic solutions. But the trick with basic solutions is if you have to be told that it's in basic solution. Right? You can't deduce it from the information. So if you're told basic solution, you do the acid solution first. And then you use a trick to convert the acid solution to basic solution. So I'll show you how to do that. Well, let's do it with this one. Let's say we got 8 hydrogens left here, right? Let's put our 8 hydrogens in. Okay. And for this one, got rid of that water. And then we have 4 waters on this side. There we go. And those hydrogens go. Okay, so that's our balanced equation, acidic solution. How do we convert this to a basic solution? You add hydroxyls to the side that has protons and neutralize them. Right? So if we have 8 hydrogens here, we need 8 hydroxyls on both sides. You can't do something to one side without doing it to the other. So we add 8 hydroxyls on that side. Okay? So that neutralizes these and makes 8 waters, right? H2O. And on this side, we have 4 waters and 8 hydroxyls. But these 4 waters go out because 4 of those are consumed over here, which means 4 H2Os net. And that gives you water on this side now and hydroxyls on that side. Now we have a basic solution balanced equation for this one. Okay? I call it the half reaction basic solution is a fake acid solution. You do the acid first, then you convert it to base. That's the most efficient way. There are methods for doing it, going straight to basic, but they're a little hard to follow. This always works. If you do acid first, then convert to base. Let's see, how are we doing on time? I want to be sure we cover all our bases. So we've come up to this point. We have a couple of other examples, but you have the slides and the animations in here. And remember, if you're asked for, remember when we were balancing equations and some of the multiple choice questions would ask you, what's the coefficient in front of something? Well, if the coefficient is, if it doesn't have a number there, what's the coefficient? 1, right? Okay, so don't forget that. Or if it says, what's the summation of all coefficients? Don't forget to add the 1. Okay. So this is another example of balancing a redox equation in acid solution. So we go through the same half reaction method. There's our reduction, there's our oxidation. Balance the elements first that are not hydrogen and oxygen for each of the half reactions. Right? Okay, then you take your half reactions, and if necessary, you add oxygens and hydrogens. In this case, well, we should have added, no, we're doing electrons first. There we go. Now we're putting in oxygens here to balance these oxygens. That means we got to put hydrogens over here to balance the hydrogens we just put in. So there are hydrogens to balance those hydrogens that we put in as water. Then we match up the number of electrons. So what if you have an odd number of electrons here and an even there? Cross multiply, right? So you multiply this one times 5 and that one times 2. And that would give you 10 electrons total. Right? 10 electrons here, 10 electrons there. So now you got the electrons balanced. At that point, you can add the reactions together, cancel common reactants and products. You have the same thing on both sides. Right? In this case, we don't have any hydrogens on that side. We don't have any waters on this side, so that's no problem. We've gotten rid of our electrons already, so that's the balanced equation. Now this one takes you to basic solution as an example. So if you got these hydrogens here, you just add 16 hydroxyls. There we go. To balance those, to turn those hydrogens into water. And then you put hydroxyls on the other side to balance the ones you just added on the reactant side. And now we have waters on both sides that we have to cancel. So there's 8 here and 16 here. Those cancel, leaving you with only 8 on this side. Okay, so same method as we used here. While I'm erasing this, any questions? Now, when do you use this method? When you know that you have an oxidation reduction reaction. So you need to determine that first. If your reaction is not oxidation reduction, just go back to using the earlier bookkeeping method of balancing. Sometimes the bookkeeping method will work for this one too, but it can be difficult. Right? If you have an oxidation reduction reaction and you try to balance it the old method, it may take you forever, or you may never get there. So if you know that you've got an oxidation reduction reaction, you go to this method. Okay. So electrochemistry is just, it's a broader, an umbrella word for redox reactions. Electrochemistry studies actual chemical reactions in which electrons are transferred and electrical energy as a process and as a product is part of the equation. So you'll have a heat of enthalpy for the reaction, right? You have a delta H that's part of the process. Electrochemistry itself also includes the concept of batteries, electrochemical cells, right? We saw that in redox reactions, you have electrons transferred, right? That is a potential energy source. When electrons are moving, If you can capture those electrons, you have a source of energy. But if you just mix them together, you don't have access to those electrons. Right? They're in the solution, you can't get at them. So electrochemistry separates those half reactions so that you can shunt the electron movement into an external circuit. Now you have access to the electrons. Right? You can either read off a voltage, or you can send those electrons through a motor or through some other process and use them to do work. So now that we've learned how to split a reaction into half reactions, we find that now it's convenient that we know that one is a reduction, one is an oxidation. We can put the oxidation half reaction over here, the reduction half reaction over here, and connect them with a wire and a salt bridge so that you have a circuit. Right? You can't have electrical current without a complete circuit. Right? If you break the circuit anywhere, you no longer have. It's like pulling the plug. So you have to have a circuit. This is an example. Right? We have one half reaction is the manganese oxide making manganese, and iron 2 to iron 3. Right? So this one is oxidized. We went from +2 to +3. This one is reduced. Let's see, that would be 7+ to 2+. And what you do is you put one of the reactions in one cell. We call it a half cell. And the other reaction in this cell. Right? And then you connect them with a wire. Okay? This is where the electrons flow. Right? So which direction are the electrons going to flow here? This is the electron donor. Right? So if this side donates electrons, the electrons have to move up that wire and over to the other side. This is the oxidizing agent. It's going to cause the oxidation of this one, so it has to be reduced. So we're reducing this manganese 7+ to manganese 2+. That means these electrons are going to come over here, combine with that manganese, and make this manganese. So in this cell, we're reducing manganese. Okay? But it's not going to work until we can complete the circuit, because those electrons are not going to move over here, because if they do, they leave an imbalance of charge on that side. So we need a bridge here to complete the circuit. There we go. Wait a minute. Where is it? There we go. So in this case, we use a salt bridge, and we have a plug down here just to keep the half cells from just wholesale mixing. We just want the ions to move. Or you can have a porous disc in between them, and that allows electrons to move through the disc and complete the circuit. Okay, let's see. What did I skip on these others? Oh, definitions. Yeah, let's go back. Come on, back. Here we go. So to complete the circuit, we need a bridge. Okay, we've already talked about that. Then we have names for them. It must be on this one. Here we go. So what do we mean by cathode? Let's see, that's green. It's not going to show up very well. Try this one. Cathode and anode. The cathode is the cell in which reduction takes place. That means the electrons are going to be on this side, the reactant side. So as we add electrons to this side, they are taking that manganese 7 plus down to manganese 2 plus. So the left-hand cell here is the cathode cell. Okay? That makes the other side, where oxidation takes place, that's the anode. And the electrons for this one are going to be on that side. So this is the anode because this is the side where oxidation takes place. All right? You just have to learn it. Cathode is reduction, anode is oxidation. Okay. Now, which way do the ions move between these two solutions? Well, if we're taking negatives away from this side, then they're going to have to be balanced by positives. So the positives are going to move from this side to that side, and the negatives are going to move from this side to that side to replace the negatives lost on that side. Right? You have to have balanced charge. If you don't have balanced charge, you have electrostatic situation, which is not unheard of, but it's anti-productive to have electrostatics in your electrochemical cells. Right? So we only produce electrostatic situations for physics purposes. In chemistry, we don't do that. Now, that's process one. That's otherwise known as a galvanic cell or electrochemical cell or a battery. This is named after an Italian, Galvani, who built the first battery. That's a case where you use a chemical reaction to extract energy. Right? So we have access to these electrons moving in this external circuit. And we can spin a fan, or we can light a light bulb, or we can drive a motor, you know, that type of stuff. Or you can just measure a voltage, or you can measure a current. The other way is electrolysis. And electrolysis is just, you run the battery in reverse. So if the electrons are moving this way, you put an external source of power that supplies electrons to drive it backwards. Right? So the reaction, when you set up a battery, you're depending upon those two half reactions to be spontaneous. That is, you put them together, they react and deliver electrons. If we run that reaction backwards, then we need an external source of electrons that are interjected at a higher voltage and drive the reaction back the non-spontaneous direction. That's electrolysis. Okay? And it's used in industry, used to be used in industry to chrome plate bumpers. You ever seen antique cars with chrome bumpers? Yeah, that's how they do it. They put that bumper in a vat with chromium in it, and they put a charge on it to run the reaction backwards and deposit metal on the bumper. That's how your gold-plated jewelry is made. Right? They stick some cheap metal, or maybe just silver, in the vat. They run the charge backwards and deposit gold metal on your jewelry. Very thin layer, but they do it by electrolysis. They run the reaction backwards. Okay, this is the reaction for a lead storage battery, the anode reaction. So anode means oxidation, right? So this lead is oxidized from 0 oxidation state to 2+ oxidation state. Right? That's one side of the battery. The other side, the cathode, is one in which lead 4+ becomes lead 2+, and it is being reduced in the process. Right? So we're transferring electrons from this side to that side. And in the process, we're extracting that energy to run the radio in the car, or run that current through the starter motor, crank your engine over. And then when you do that, you partially discharge the battery. You use some of its energy. So that the battery doesn't continuously discharge, we have an alternator hooked to the engine. So once the engine starts, it runs that alternator, and the alternator supplies electrons to drive those reactions backwards. And that's called charging the battery. You put it back to a state where it has all the lead is returned to this condition, and all the lead sulfate is returned. Well, the lead sulfate comes back to this one for that cell, and it comes back to this one for that cell. And it's ready to run again at full charge. The nice thing about the lead acid battery is the lead plates and the lead oxide plates can be suspended in the same solution. You don't need a salt bridge because they have a common product. Okay? And they're both suspended in sulfuric acid. Right? So that's one of the conveniences of the lead acid storage battery, is that the cells can be together in the same container. And you can measure a voltage for each one of these cells, and each one of the cells is 2 volts. Right? So does anybody, I've asked this before, no physics majors in here? Okay. It's characteristic of circuits. If you combine a circuit in series, right, if you have 2 volts in this one and 2 volts in that one, and you connect them in series, right, you get 4 volts. Because this one's pushing with 2 volts and this one's pushing with 2 volts. They add up to 4 volts. So for a 12-volt battery, you just need 6 cells, 6 electrochemical cells in series, and you get 12 volts. Okay? Some diesel engines and some tractors have more voltage, like maybe a 24 or 48 volt battery. You just stack more cells together, and you get the voltage that's required to turn over a big diesel engine to get it started. Sometimes you need more voltage to make them turn. Okay. This is also a situation where you have the 2 plates. You have the lead plate and the lead oxide plate together with sulfuric acid in between. And when they discharge, when you extract energy, you're producing lead sulfate, which is a solid, on the surface of your plate. Okay? The problem is, being a solid, it's not in solution, right? So the reaction takes place at the surface of the solid of lead sulfate, and through several hundred or thousand cycles of charge and recharge, discharge and recharge, you get this lead sulfate built up on your plate. And eventually, you get so much built up that the solution now no longer has access to the lead underneath and the oxide underneath of that one. And at that point, your battery's dead. It cannot be recharged, and it's said to be sulfated out. The only thing you can do is replace the battery, send that one to be recycled. So if you've got a lead acid battery that will not charge again, well, 2 things could go wrong. It could be sulfated out, or it no longer has sufficient concentration of acid to complete the reaction. Now, the batteries we have in our cars these days, and some lead storage batteries that are used in other pieces of equipment, are sealed. It used to be that you couldn't seal them because in the process of recharging, they produce gas, hydrogen gas, and they would explode. So they always had these little vent holes in them. And the process of producing, of running the reaction backward was you produce a little bit of hydrogen gas instead of just hydrogen protons. And you need those vent holes to get that hydrogen out of there so your battery doesn't explode. But now they've got technologies where you can seal the batteries, and they have an absorbent in there that will suck up that hydrogen and release it back slowly. Right? So sealed lead acid batteries are common. It used to be you'd have to go to the service station periodically, and they just stick this little tube down in your battery. They pull up some of the sulfuric acid, and it would read it off whether it's strong enough. Right? It was using a hydrometer because the density would change. And then if you needed some fluid in your battery, they just add distilled water to it, and then check it again, and to be sure that the acid concentration was at the right point. And if it wasn't, then what they could do is add sulfuric acid to your battery and build it back up. And usually that'd make your battery last longer.
So they had sulfuric acid on hand at the time?
Yep.
Wow.
Yeah. So they had to be trained to use it because it's concentrated. I don't know if it was 98%. You can get sulfuric acid 98%, which is really dangerous. It could have been at a lower concentration for commercial use. But that's what they used to do. Now they don't have to do that because the batteries are sealed. Okay, let's see what else we got on. We'll talk about just a few slides more on batteries, I think. This is what one looks like. Actually, one cell of a battery. Electrical potential. That's another word for voltage. Electrical potential is voltage. Is how hard is the chemical reaction pushing electrons? Higher the voltage, the harder the push behind those electrons. Dry cell batteries are not really dry. They're more like a paste, right? And you know, if you have a dry cell battery that has been in storage too long, or you leave it in your electrical device too long, it starts leaking. You'll see this crystal stuff collecting on the outside. You want to use gloves, remove it, clean it out, because it's corrosive. The pH is, most of them are basic, so the pH would be greater than 11.5. It could be hazardous. Or if you do want to stick your bare hands in there, be sure and wash them quickly before it has a chance to react. Dry cell just means it's not a liquid. I mean, it's not like a solution that you could just dump and pour out, but it's still moist. There are acid versions and basic versions. The zinc cell, the zinc is usually the battery casing is made out of zinc. So that's your anode. And then the cathode is actually buried in the middle, and you have this carbon rod going down in there. So when the battery has batteries built like this, where you have the flat side with kind of a dimple and then a hump on that end. All right, so this, let's see, which is the negative? This is the negative side and this is the positive side. So this one is usually connected to a carbon rod. And the carbon doesn't enter into the reaction. It's just a means to transfer electrons. So the casing is made out of zinc. And then you have, this is your anode. And your cathode is here with the reaction in there, around that. And it transfers the electrons from here to there once you connect the circuit. Right? Once you put your battery in, then it'll transfer electrons from the anode to the cathode. Okay? And that's your zinc dry cell battery. Well, there's the alkaline version. There you go. So there's your graphite rod. There's the zinc. And of course, we cover the outside, right? We don't just leave the zinc bare. We put a coating on the outside so you don't short circuit your battery. And there are various forms of dry cells. There's a silver cell. You'll see those a lot in hearing aid batteries and calculator cell batteries. The mercury cells are not very common anymore, simply because mercury is hazardous. So we've done away with those. Nickel cadmium is a rechargeable. The rechargeable cells are designed so that when you run them backwards, you don't create situations that eventually degrade their performance. They're built to be recharged many times. The dry cell batteries are built to not be recharged. I know you can do them, you can run them backwards, but they're not very efficient at it. So this is an engineering problem. But nickel cadmium used to be very common in rechargeable devices. Like I've got a little beard trimmer that has a nickel cadmium battery in it, and it's about at the end of its life because I can recharge it, and it just, I've had it for 25 years, so it's time to get rid of it. So these are not used very much anymore because they have a memory effect. In other words, if you discharge them, say halfway, and then recharge them, they reset themselves. And they think that that half charge level is the bottom of the barrel. They think that that's zero, so they won't go any further below that. So what you do is, for those, you set them on, just turn on your device and let them run all the way down to dead. And that resets your bottom. And then when you charge them back up, it knows that bottom is really bottom. Now, I've done that several times with my little trimmer, but it doesn't work much anymore. So, now this is not very common. What we use most often now are lithium-ion batteries. They take some special circuitry because when you start recharging them, if you go too far, if you overcharge them, you're introducing a reaction that wasn't meant to be. You're driving the reaction too far past its base situation. And you can cause them to explode. Right? So you have to have advanced microcircuitry in there to know when it's reached the right point and it stops charging. So every lithium-ion battery has a built-in circuit board in to know when to stop charging. So you can hook up your computer, your laptop, and just leave it hooked up, or your phone and leave it hooked up. As long as that circuitry is working correctly, it'll stop charging at 100% and won't go beyond. Corrosion. Corrosion, in the simplest terms, is just another word for an undesirable electrochemical reaction. So if you just bury an iron pipe in the ground, like sewer pipes, they used to be made out of iron. Actually, it's an iron alloy. Eventually, they will convert to rust, iron oxide. So how do you prevent that? Well, you connect a metal that will corrode more readily than your iron pipe. And what it does is it takes electrons. When this corrodes, it is being oxidized, so it delivers electrons from that process to the pipe and keeps the pipe as iron instead of iron oxide. Because iron oxide is an oxidation process You want to drive the reaction backwards. So you have a sacrificial anode that supplies electrons to this pipe and keeps it from corroding. You'll see ships, they'll have this band of zinc wrapped around the ship. And it's there as a sacrificial anode to keep the ship from rusting. So the zinc will oxidize more readily than the iron in the ship and provide electrons to the iron to keep it from converting to iron oxide. Now, when the ship's powered up, they trickle electrons into that zinc so that the zinc doesn't corrode away too. Right? But when the engines are turned off, the zinc functions as it should. And then when they provide electrons to it from the ship's engines, then it provides those electrons through the zinc to the iron and keeps the ship from rusting. Every water heater has a sacrificial anode in it. You know that? It's usually aluminum rod, about that big around, goes from the top all the way to the bottom of the tank. And the reason I know that is, as it corrodes and protects your pipes from corrosion, it converts to aluminum oxide and flakes off of the electrode and settles in the bottom of your tank. So if you have an old tank and you watch the tank being changed out, you have to drain it. Then as you open the tap, you see all these little white crystals come flowing out the tube. That's your sacrificial anode that's been converted to aluminum oxide. The reason I know it's in there is because the first tank I had in my house, I noticed that my dishwasher was not running right. So I looked and it has a little filter in there. So I pulled the filter out and the filter was just a little metal cage. It was just covered in those white crystals. So it was sending those crystals through the hot water line, being caught in that, and the water wasn't getting into my dishwasher. Right? So then I knew to go down and check. So I pulled it out, and it was just corroded all to hell. So instead of being this long, it was about that long and just pitted all over. So I went to the hardware store and got a replacement electrode and stuck it in there, and we were good to go. So this cathodic protection is widely used. Right? And aluminum is a good one because aluminum's cheap. It used to be aluminum was more expensive than gold because it was hard to make. But once we figured out how to produce aluminum cheaply, you just need a lot of electricity. Now aluminum is really cheap and we can use it to wrap our foods, throw it away, or make cans out of it and throw them away or recycle them, whichever you prefer. Electrolysis can also be used to split water, produce hydrogen gas and oxygen gas. So the natural, spontaneous way that hydrogen and oxygen behave is to go backwards this way. Right? You mix hydrogen and oxygen together and provide just a little bit of bump, like a burning ember or something that'll go pow, just immediately. And the reaction is electrochemical. Right? Oxygen goes from 0 to -1, hydrogen goes from +1, goes from 0 to +1. So we know that's a redox reaction. And we used to send a space shuttle into orbit using that reaction in reverse. It goes from here, that way.
My sisters still don't believe that that's how spaceships get to space. If that can't be water.
Yeah.
Keep going.
But this is also the holy grail of renewable energy. If you have an unlimited supply of electricity, you can split water into hydrogen and oxygen and use those in your vehicles. Right? So if you have a fuel cell, you can run hydrogen and oxygen into that fuel cell. This is usually the fuel, and you just take oxygen from the air and produce an electric current by that reaction and run the motors that drive the wheels on your car. But the question is, where does that electricity come from? If it comes from a renewable source like solar power or an unlimited non-polluting source like nuclear, then you're good to go. Right? But if it comes from a fossil fuel, then it's no better than just burning fuel in your engine, right? Producing carbon dioxide and whatever other pollutants come out of your engine. But if we can find an unlimited source of electricity, then this would be the way to go. Like fusion power. Solar and wind, there's no way they're going to give us enough energy. No, it's too diffuse. You'd have to cover the globe in photovoltaic cells just to meet our present needs. So nuclear is the way to go. If you want to know if someone is really serious about this climate change thing, ask them if they're for or against nuclear power. If they're against nuclear power, then they're fakes, because that's the only way to go to be non-polluting and produce all the energy you need.
Aren't they still talking about getting nuclear fusion, I think it is, in the next like 30 years?
They're still working on it.
And I know they've come up with a lot of different ideas.
They come to the point now where they can get the same or just a little bit more energy out than they put in.
Yeah, I've heard that. And you're like, it's so close. Why?
Yeah.
But
So
I've heard so many benefits about it, like how it doesn't produce any toxic waste, that kind of thing. It's so reusable. It's really safe.
yeah,
You just need to figure out how to make it worth it.
right,
So, I'm
right.
for
And
it.
you don't get it. You can't have a China syndrome with fusion, because once your power goes down, it just shuts down. You've got to continuously put power into it to keep the thing going. And if that shuts down, then it just stops. And we've got an unlimited supply, virtually unlimited supply of deuterium in the oceans. And that serves as the fuel.
And my brother's still hoping for it. That's his thing.
We'll get there eventually.
He says, well, he knows we're going to get it. We just don't know when.
It might not be in my lifetime.
He admits that too.
Okay, so is that the last slide? That's the last slide. Okay, so jump into those review problems, and we'll work on them first day we get back. Next week you're off. Okay. I'll be around, but if you need to come by and see me, text me and be sure I'm here. Okay, we can shut her down now. Stop the recording.